Good morning. Good morning to you all there at Manchester. Welcome to my presentation. In this talk entitled Differential Compaction and its Seismic Attribute Expression, I'm going to talk about differential compaction as such and how we can recognize it with the help of seismic attributes. You see, to begin with, let us clarify the term differential compaction. The term compaction, as it refers to sediments, implies that a layer of an older sediment is under the effect of loading of one or more sediments, or shall I say younger sediments, and this increased loading results in the older sediments getting compressed. This process of compression results in the older sediments getting losing their porosity as they are compressed, which depends on the particular lithology we are talking about. Now we are aware, as we have seen many well-log curves from a well, the sonic, the density or the porosity, they all show increased velocity, increased density, and porosity reduction with depth. So that is compaction. The other term, differential, refers to the varying amounts of compaction that may take place in the older sediments. Of course, the variation in compaction would be dependent on the thickness and the lithology of the older sediment. So thus, differential compaction refers to the difference in the extent to which a sediment is compacted. For example, the compaction suffered by a certain thickness of a shale sediment would be different than a similar thickness of a sandstone sediment. So that is about the term differential compaction. Now, the differential compaction also depends on the topographic irregularity on the surface on which the sediment sediments are deposited. So essentially, that is what we are talking about here: the difference in the irreversible change, volume change that the rocks suffer under pressure, which comes from the weight of the overburden or the sediments deposited on them. The next thing to talk about is what are the effects of differential compaction. Well, differential compaction can cause a drape over sand bodies and reefs, and this is caused by the fact that the sand body or the reef, they do not compress to the same extent as the shales. As you may have followed till now, these drapes these drapes are caused not by any tectonic activity, but are formed by the sedimentary process itself. So, why is differential compaction important for oil and gas exploration? It is important because such drapes can form closures which can trap hydrocarbons, and so for us that is an important aspect that needs to be considered. Typically, differential compaction has been observed where, for example, an erosional unconformity of considerable topographical relief has been covered with a compactable sediment. Shale bodies that contain lenses, sand lenses, carbonate reefs that are embedded in shales, or when we have pure shales grade into sandy or limey shales. This last one is an example where the compactability of the material itself changes. I hope that is clear. On this slide, you see the steps that show how differential compaction can take place. For example, in the first one, we have the early water flooding phase when the silty and the clay sediments they were deposited. Number two, the drain phase, when the water got drained out and streams flowed across the former riverbed and resulted in valleys where sand could get deposited. Number three, once again the river gets flooded and more layers of silty and clay sediments get deposited over everything. And finally, number 4, the river again gets drained for the last time. The sediments dried, but due to the less compacting sand, the sediments drape over it and form a compaction ridge. So that is, how differential compaction can take place. Large volumes of sand can be injected from the already deposited sand bodies into the overlying shale sequences. And such a situation is usually seen in deep water clastics. These sand injectites, as they are called, they are seen emanating from the edges of depositional sand bodies, as shown in this cartoon that you see on the screen. So such reservoirs are seen cross-cutting depositional stratigraphy and have a variable thickness, as the injectites form what we call dikes or sills or other geometrical shapes showing up similar to the igneous intrusions. Now, the wing-like reflections from the edge of the sand are usually seen on the seismic data and are interpreted as low-angle sand dikes. The dikes or sills could be somewhere in the range of 25-30 meters thick, but what you need to notice here is the differential compaction has altered the shape of the sediments above, as you see here. So that's strictly the effect of differential compaction here. Similarly, the sediment drapes can be seen over reefs, and this picture that I'm showing on the screen is self-explanatory. Differential compaction occurs in the reef, in the zone where you have the reef interval, shall I say, and the vertical expression of the drape features becomes smaller gradually with height, and so that is something we need to look for. Now, there is a lot of work that has been carried out on differential compaction, and it starts way back in 1979. This is the reference by Bubb and Hattleded from the AAPG Memoir 26, I believe. And so this is a classic article that showed differential compaction and pull-ups to be the key means of identifying the subtle carbonate buildups. So now let's have a look at an example from this particular reference. Now this example is from North Africa, and they were using 12-fold data at the time, and it shows a pinnacle reef that is interpreted on the seismic section by the on-lap reflections, and you see some of those on-lap reflections on the sides. And drape in the overlying sediments, as you see that drape up here, and the slower velocity pull down below the build-up, and you can see some kind of effect of velocity pull down below the reef as well. Now these are seen not only at location B, it is seen at location A as well. So location A was drilled first based on some older version of the seismic data, and it encountered 60 meters of gas-filled pay. The well was not considered economic enough at the time and was abandoned. Now, subsequently, the acreage was picked up by another company, and by using high-quality seismic data for their interpretation, they drilled well B. Now, interestingly, it encountered 300 meters of porous limestone, and oil flowed at the rate of 40,000 barrels per day, and the estimated reserves were 1.5 million barrels of oil. So this was a very successful example that was published way back in 1979. And there's another reference, Heritier et al. In the same memoir, and in 1980, and that also recognized the differential compaction over sand pans in the North Sea. You see, the Frigg field is the world's largest offshore gas fields, and is located between the UK and the Norwegian continental shelf at around, I believe, 60 degrees north latitude. And the first well was drilled there in 1971 in 100 meters of water. This Eocene Frigg sandstone formation is the main reservoir of the field and is located at a depth of 1850 meters. The total recoverable reserves of the field, they were 192 billion meter cube of gas at a recovery rate of 78% over its lifetime. Of course, the field was shut down in 2004 after 27 years of production. The contour map that you see on the top in the slide shows the Frigg field, Frigg sand in the dotted area, and it represents a submarine fan reservoir which encloses an area of about 115 square kilometers. The sand influx in the area by way of channeling and fan system and the ensuing tectonic activity, followed by further deposition, led to a sand redistribution. So most seismic sections across the structure, they show a flat spot, which is the reflection from the density contrast of the gas and liquid contact within the reservoir. So with a shale unconformity above and more shale deposits below, the levees at the time of deposition, they were differentially compacted, and the sand deposits on the flanks of the original levees, they are now seen as topographic highs. So that is this another successful case study where we see or we talk about differential compaction. Then, there were other references, and one can always pick these up, Possamentier and Allen and Elvis and Cartwright and others. And we can have a look at this reference, an example from this reference from Brazil. You see, with the petroleum exploration and production going into deep water depths globally, and also the availability of high quality seismic data sets, the mass transport deposits, they are now recognized as a major component of slope systems and most deep water settings. The remarkable spatial resolving power of the 3D seismic method can definitely be used to define the full aerial extent and the morphology of these mass transport deposits, or the MTDs as they are called. And the precision that this can be done with, it cannot be achieved with any other combination of methods. So on this slide on the left, you see a coherence slice showing the MTD and the marginal strata from offshore Brazil, as I said earlier. And you can see the inferred path of the failed strata when they flow in the downward direction. To the right here, we see an east-west seismic profile that shows differential compaction over the heterogeneous MTDs well after burial. So differential compaction can take place in different settings. And finally, there's a reference, Bukowski and McGill, who showed that differential compaction models, using differential compaction models, that topographic depressions form over buried impact craters. Now, here is an example of a laccolith where you see a sheet intrusion injected between two sedimentary layers. That is, the magma is injected at high enough pressures to force the strata upwards. And an example of a laccolith is also, I picked up this example from the Wikipedia on the internet. It is exposed by erosion of overlying strata in Montana. But let's get back to our seismic data and how 3D seismic data, and how we can detect differential compaction with the help of seismic attributes. You see, the seismic attributes that we are going to talk about here, they are coherence and curvature, which are also referred to as the discontinuity attributes, and they are routinely used in mapping structural features such as folds and faults and flexures. As differential compaction gives rise to the deformation of overlying sediments, we will see how we can use them to map the features of our interest. And we will also see examples of positive relief, sand-filled channel features in a shale matrix, as well as the negative relief, compacted vinipigosus carbonate buildups in a salt matrix in the Western Canadian Sedimentary Basin. But before I go there, let me give you a brief, an intro or a description about what are we talking about here in terms of coherence. Essentially, coherence measures the similarity of seismic traces, adjacent seismic traces, and in the process it images the discontinuities in our data and reveals the structure and the stratigraphic changes such as faults or channels or reef edges or fault truncations or whatever the case may be. Now, in all these examples that I'm going to show, I will use a particular color scheme. But before that, let me mention that because this coherence is a similarity attribute, on the upper image, what I show is a coherent reflection. That means the trace-to-trace similarity along this reflection is going to be high. But if you look at the lower image, from trace-to-trace similarity in the highlighted zone, the coherence is not going to be high because the waveform is changing shape laterally. And in most of the examples that I will show, we will look at low coherence values depicted using black or dark gray color, and high values are seen in white or light gray. Now, coherence is a three-dimensional process, and it needs samples in each of the three directions. As I show in this cartoon here below, you have three samples shown picked up in the inline direction, three samples in the cross-line direction, and a certain number of samples in the time direction, which can be utilized for the computation of coherence attribute. Now, how good is this? Why should we use coherence? I mean, one needs to be convinced of this. And so I'm showing you time slice at 1333 milliseconds from a seismic data volume. And if you look at this and try and pick up features, the discontinuity features that may exist, well, you can probably say, well, there is probably something here, maybe channel-like feature or something going on here, but there's not much forthcoming out of this. But if you look at the equivalent coherence slice, there is a lot of information there. You have a main channel that runs almost east-west, and then there are vertical channels as well. So this is the amount of information, the subtle information that can be picked up from the seismic data volumes, which otherwise only on the amplitudes we may not be able to do so. Here's another example from the Gulf of Mexico, and this is the seismic time slice. But if you look at, of course, if you examine this closely, you see some of these circular features here. There are some channel features here. Looks like this is also a channel. There are some faults. But if you look at the equivalent coherence slice, you see there is a lot of information that can be interpreted. And so coherence is a useful attribute, and one needs to be convinced to be able to make sense out of it. Here's another example from the Gulf of Mexico. On the left is a seismic time slice, and it's not very deep, 1184 milliseconds. And to the right is the coherence showing a channel system at different levels. Now, what are the different algorithms available that can be used for this? Well, we have the cross-correlation algorithm, which was the very first algorithm that was introduced back in 1992, I believe, and published in the Leading Edge in 95, October issue. Then, of course, there were improvements over this algorithm. We had the semblance algorithm, variation of that is the variance attribute. And then we have the eigenstructure algorithm, and there is also the gradient structural tensor attribute. This eigenstructure has also given way to another variation, which is referred to as the energy ratio algorithm, and that is what I'm going to show you here in some of these examples. First, comparison of the coherence algorithms, and as you see here, we have the seismic time slice on the top left. We have the cross-correlation coherence shown on this top right, and then we have semblance lower left, and then we have the eigenstructure on the lower right. Notice the amount of information that this eigenstructure algorithm is furnishing. It is not only the main features in terms of the faults, but very small subtle features. They are also seen in all its clarity. So this is the difference in the algorithm performance on the same input data. And a variation of this eigen decomposition or eigenstructure algorithm is referred to as the energy ratio algorithm. And notice here is a comparison of the semblance, energy ratio, and the eigen decomposition. And as I show at some of these places, you can see the difference in the performance. Look at this. We have a doublet here, and there's a single lineament here, and similarly you have a feature which is better defined here as compared with this one, and so on. So it obviously has advantages over the eigenstructure algorithm. Here's another example where you have coherence eigen decomposition on the left and the energy ratio to the right, and notice wherever the arrows are there indicating a better performance, crisp, better definition, focused definition on the energy ratio algorithm. And here is yet another example where on the top we have one, and there's another one below. These are time slices that we are looking at, but the energy ratio coherence algorithm performs much better than even eigenstructure. Here is an example from the North Sea, where I have the seismic time slice on the top left. And of course, we are looking at time slices at 1240 milliseconds. And here is the coherence semblance algorithm. But look at the energy ratio performance. And then these are polygonal faults that are seen at this level. And one of the versions or the explanations given for the formation of polygonal faults is the dewatering of overpressured shales. So whatever the reason may be, but we are looking at these in these polygonal faults, and they can be correlated with the seismic data, and you can do this on your workstation with the help of the cursor connect options, or you can bring them up in separate windows, and then you can look them up, or you can generate chair displays with the horizontal as the coherence and the vertical as the seismic, and then you can correlate one with the other. But before we compute these attributes, we also need to be aware of the noise in the data. For example, on this section, I'm showing you a segment of a section from the input seismic volume, and there is a lot of jitter in the background that you see there. But if you run a filter on this to remove the background noise, such as a median filter or a mean filter, of course, or the structure-oriented filters that are available these days, you can tone down the background noise. And here I'm showing you an example where a 3x3 median filter, which is following the depths of the reflections, that has been run on the data, and notice on the output there is a better signal to noise ratio. When this data goes into the generation of the attributes, this is the kind of difference that can happen. Before conditioning, after conditioning, there is a lot of difference in the background noise in terms of the incoherence in black. But these days, the structure-oriented filtering process is available in most workstations, or shall I say the software is available on the interactive interpretation workstations, and so they can be utilized for cleaning up the data. On the top left is the seismic time slice, and to the right is the same time slice after structure-oriented filtering. Similarly, the coherence on the same data shown below, and after filtering is shown to the right. Notice the clean looking version that you see there. Also, in the presence of dips, one needs to compute coherence along the dips of the reflections, and we refer to this process as the dip steering option. If we do not do so, we can see these contours on the coherence attribute or the slices that we may generate from there, time slices or whatever, and look at these the contours. They could interfere with our interpretation. So if we compute coherence along the depths of the reflections, or we adopt the dip steering process in our computation, we can get rid of all these artifacts, and we can get a much better looking displays. Here's an example from the ABQAIQ field, south area, and of course it forms part of the GHAWAR field, which is the biggest field in the world that is producing oil. And this ABQAIQ field, it shows a domal structure, as you see on the cartoon below. Vertical section passing through that shows a number of faults that have been picked up on the seismic data, and the level of interest is somewhere down here under the Arab D and the Hanifa or in the Hanifa zone. Now, on this on the left is a structure map that was generated based on the well log data available, and in the middle is the same structure map but extracted from the interpretation, or it was generated from the interpretation that was carried out on the 3D seismic data. And notice the number of faults that have been picked up on this. And then to the right is the same interpretation that was done on the coherence data. And now you see the amount of detail that has been picked up. So that's the level of detail that we are talking about when we start using coherence in our interpretation. And of course, when we have data which has missing traces, in this particular case, I'm showing you a segment of a part of a 3D seismic volume which has a number of traces missing on the traces as it is animating. Now, if this data goes through the coherence computation, you can get this kind of a display where you have the missing traces seen in the form of these black squares. Now, if you tweak your parameterization, you can get a better display. Like, for example, I show you on the left the same data but with a number of these dots showing the missing traces. Now, what we can do is during processing we can get rid of this artifact, and that we can do with the help of what we refer to as the 5D interpolation. That means it interpolates data in an intelligent way in 5 different dimensions, and then gives us some data that we see missing in the input. As you see to the right, there is a lot of definition that has been brought about. The channel system looks much more coherent, and the missing traces they have been filled up. So in a nutshell, the conclusions that I draw here are using the coherence dimension to your seismic data, or bringing the coherence dimension to your seismic data enables you to see the stratigraphic features, faults, and fractures better. And adding the coherence dimension to your data is important. And I finally say that if it is worth doing well, it's worth doing coherently. And with this, I complete this part. Now let's move on to the other attribute, that is the curvature. Curvature attribute, which is a measure of the degree of bending of a surface. So on a 2D, or shall I say on a curve, we can quickly go about the simplest definition that is given to the curvature attribute. As I said, curvature is a degree of curvedness. And so if we are able to draw a circle at the point of contact, so that the circle is tangent at the point of contact, then the radius vector for that circle, if we measure, the reciprocal of that will give us the measure of curvature. Now, if we just overlay all these different radii vectors along the curve at different points, you notice that for the horizontal and the dipping planes, all these vectors are parallel, because there is no curvedness associated with these. But if you look at the anticlinal shapes or the synclinal shapes, in one case the vectors diverge and we assign a positive sign for that. In the other case they converge, we assign a negative direction for that, or negative curvature for that. And so we can associate anticlinal shapes with the positive curvature, synclinal shapes and negative curvature, and that is what we normally do. We can extend this simple definition of a curve to a three-dimensional, or a three-dimensional surface. And the way we interpret this is that we can imagine a vertical plane that is intersecting the surface along this curve that is drawn out. And similarly, this is in the direction of maximum curvature, and similarly we can have another orthogonal, in the orthogonal direction we can have a plane, vertical imaginary plane, intersecting the surface along this curve. And we can measure the curvature along these curves. But practically what we normally do is we pick up a small portion of this data, shall we say a 3x3 or a 5x5 sample aerial surface, and then we try and fit a polynomial as I show here on the top, this equation which has a number of these coefficients A, B, C, D, E and F. So once I do this, I'm able to determine all these coefficients, and I plug in these values in the different definitions that we have. For example, I'll focus more on the most positive curvature and the most negative curvature attributes here. And as you notice, first of all, we know the values of all these coefficients. We can plug in the values and determine them. But the important thing here is to know that the most positive curvature essentially refers to positive curvature values being accentuated at the cost of the negative values, and negative curvature values accentuated at the cost of positive curvature values in the most negative curvature. So if I show you a picked horizon to the left, when I run one pass of a mean filter to sort of smooth it, you can see that performance in the middle, and one pass of a median filter is shown here. So notice there is a difference in the performance of these two filters. This appears to be more crisp as compared with this one. So similar is the case with the curvature that we may compute on a given horizon. We can compute curvature with the data as the input as such, and then we can compute the same curvature measure from data with one pass of a mean filter, or a one pass of median filter, two passes of mean filter, two passes of median filter, and similarly 3 passes. But notice that with each subsequent pass of the filter, we are losing some information, the discontinuity information here. Similarly, we are losing that information here also when we have the median filters run on the input surface. But what is important to note is that with the median filter application, we are still seeing many of these features intact, which we may not see on the data with a mean filter. So with that in mind, let's move on to the volume curvature, because we may not be able to pick horizons exactly in our zone of interest all the time. And that again depends on the data, the particular level we are looking at, and so on. So again, talking about the curvedness of the reflections, notice if you have dips that are seen like this, you can draw a large circle, and this will show you smaller values of curvature. Something like this is showing you reflections that are more curved, and so it is showing you smaller radius for the circle, and that means it is more curved. Now, for the volume computation of curvature, we that is of course possible, and that work has been done by Earl Dostry and Marfut, published in Geophysics in 2006. And the equation that they make use of is shown here. But the important thing to note is they also introduce a fractional index alpha in their computation. And what gives this does is this allows them to compute curvature at different curvature with different levels of detail. A smaller value of alpha gives rise to what we call the long wavelength measure of curvature, and a higher value of alpha gives rise to a higher detailed or high resolution measure of curvature. Keep in mind, mathematically speaking, curvature is a second order derivative type of a computation. And so what this the implication that this has is that if we have noise in the input data, it is going to boost up, the curvature computation is going to boost up the noise as well as the signal. And so we need to tone down the noise if we can, as is seen here with structure oriented filtering. On the left is the input data, and on the right is the same data, but from which the background noise has been reduced, and also we see that there is a certain level of sharpening that takes place, sharpening of the discontinuities. So imagine if this data goes to the attribute computation, obviously it is going to give you better results. Similarly, on the time slices, I am showing you on the input, the input is shown on the left, and the same data is shown to the right, looking a lot cleaner, and the many of these blobs that you see in blue and red, they are looking more distinct. And here's another example, again the same thing, input data on the left, and the structure oriented filtering that we also refer to as PC principal component filtering, shown to the right. Now when we compute most positive curvature volume, then we can pick up or we can generate a slice, horizon slice or a time slice at any given level. So this is a 30 millisecond most positive curvature slice 30 milliseconds below a tracked horizon, and similarly the negative curvature corresponding to this. Notice wherever you have nice strong red lineaments on the positive curvature, they are seen as broken down reds on the negative curvature lineaments, but the lineaments corresponding to the downthrown sides of the faults, they are seen as nice and bright blue. So just a comparison between the positive and the negative curvature generated on the horizons. For example, here is a horizon picked up on a 3D volume, and here is the most positive curvature computed on the horizon, and similarly negative curvature here. Now, if you examine these two slices closely, well, you will be confused as to how much value it is adding to our interpretation. But if I show you the equivalent slices from the volume, this is the volume computation shown below, and on the top is the same set of slices I showed in the previous slice, which are computed on the horizon. Notice this is more robust. The volume computation is more robust, and that's why you see some different features on this as compared with what you see on the surface computation. And if you go down a few milliseconds above or below, you will see something different. So most positive curvature horizon slice 36 milliseconds above the picked horizon. It shows here, and similarly the negative curvature and the channel system is seen nicely on the equivalent coherence slice strat cube. Now, in terms of the low resolution and the high resolution versions, notice I'm showing you for the same data. As you see here, long wavelength and short wavelength for the positive, long and short for the negative. But then the question that comes to our mind is how much value is the short wavelength version bringing to our interpretation? So maybe in the form of when we are looking at the channels, the long wavelength version is good enough, and the short wavelength version shows us those features a little more crisp in detail, but they do not add a lot of value for this interpretation. But when it comes to the definition of the faults and fractures, subtle faults and large fractures that we may see on the seismic data, that can be seen very nicely on the high resolution or the short wavelength version, and that is very useful. So here's another example where I'm showing you coherence, most positive curvature, long wavelength and short wavelength, and notice the amount of detail that we can pick up on the high resolution version, and that brings value to our interpretation. Now again, I showed this example in terms of coherence in the previous presentation, in the previous coherence set of slides, and notice on the curvature, it again shows us those missing traces in the form of these white dots. But when we do this 5D interpolation on the data and then perform the same computation, we get something like this. Now notice this is a somewhat smoother picture that we see here, but that is not the case on the slice that we see on the left. But that's all right, because we can get away with this. And here I'm showing you the same data, but with the negative curvature display. And again, the same thing, those missing dots and the display that you see on the right shows we are adding value to our interpretation. But when we generate the short wavelength version, notice there is more detail on this that we can bring about, and similarly on the negative curvature. So the slight smoothing that you see on the low resolution version, it should not be taken as a cause of concern, because we have a measure that can give us more detail from the same data. And one thing more that we can do or benefit from is we can pick up the lineaments, positive or negative, on the curvature displays and in our zone of interest, and then generate what we refer to as a rose diagram, as I show here. These yellow lineaments have been picked up on the slice, and they have been transformed into a rose diagram. Similar rose diagrams can be generated with, or they can be picked up from the image logs, and then this rose diagram that you see on the right, this can be compared with that rose diagram that you get from the image log to get confidence in your interpretation. Now, we are looking at 100 square kilometers of this data here. So it may not be advisable to just generate one rose diagram for the full area. You can pick up generate rose diagrams at different levels, and that is what you see here in different compartments. Yellow on the left, and then you have middle one showing a rose diagram in green, and the one to the right is in red. Notice there is a difference in the rose diagram rose diagram displays, and these can be compared separately if you have image logs in these different compartments. So what have we talked about here? We said use of curvature attributes enables us to see the faults and fractures much better. Subtle faults and fractures that cannot be detected with coherence can be detected with curvature attributes. And so just like the one before for coherence, when we add the curvature dimension to our data, we are adding value. And similar again to the previous one, if it is worth doing accurately at this time, it is worth doing with the use of curvature. And so with this, let's get back to our main presentation here. So now that you have an idea about the coherence and curvature attributes and their performances on the data and what all you need to do and how they can add value to the interpretation, let's move on. So here I'm showing you a cartoon for an incised channel. You see the levies, and then you have the Thalweg. So we assign positive curvature on the levies because this is anticlinal shape, similarly anticlinal shape, and negative curvature to the Thalweg, and so that is positive and negative signs that you see there. But if I look at this channel, I mean in a 3D sense, for example, this will give you an idea of a channel. So I'll say, well, this is a positive curvature lineament that I see on the two sides, and that will be the negative curvature lineament that I'll see at the bottom of the Thalweg, and this is fine for an incised channel. But when it comes to differential compaction that may take place on the data, you notice now differential compaction gives me a shape that has a negative curvature on the levy, that is on the two sides, and there is a mound on the top which is showing us a positive curvature because it has an anticlinal shape there. So on 3D data, this is what we see. We see in this particular display, we are looking at a coherence strat slice or a horizon slice, and the vertical slice is the seismic. And I notice here we have the two levies on the sides, not very well defined, but still they are there. And then we have the Thalweg defining the channel. So we are going to see the positive and the negative on the slices on the display correspondingly. Here is an animation that is showing you an incised channel, and then the seismic is showing you have a nice looking levy on the right hand side, and the one on the left also is there, but we can make this out. Again, a strat cube from the coherence, which is shown intersected with the segments of seismic sections, and what we notice here is that notice here this incision of the channel is deep here. And by the time you come here on this meandering channel, you do not see it so deep. It is somewhat less, but when you come here, there's hardly any incision, very small. And it still defines the incised channel for us. So as you see here, deeper incision here. By the time it comes here, less incised, and this one is even less. So we can go through this. And if you look at the amplitude, if you pick up the vertical slice that I've shown there, but use transparency on the positive and negative curvature and bring the two together, you see the levies are not very well defined everywhere. For example, on this meandering channel, at places the levies are defined, and at places they are not. And similarly, there is another channel here that is coming this way, and that is a slightly lower level. But sometimes when the channels are differentially compacted, as I said before, you may see positive curvature on the top of the mound, and that is what I show here. So this is a differentially compacted channel, and on the two sides we see this is coherence in black that has been brought on this into this display using transparency, and this is the signature of a differentially compacted channel. I'm showing you some more examples from the positive curvature. Notice what the differential compaction looks like on the positive curvature, which otherwise on the incised channel would have given you the two levies. But here it is showing you that the compaction, the top of the compaction. And the negative curvature is essentially showing us the edges of the channels. So in one data set, we notice we have incised channels, as I show you here, this one, and similarly here. They are signatures of incised channels. But look at this. This is a signature of differential compaction or a differentially compacted channel. And this is just turning the same strat cube to one side. Notice the differentially compacted channel looks like this. But these channels that you see here, they are incised channels and they look different. And here is a comparison of all three, where you have positive curvature shown in the middle, negative curvature to the right, and coherence to the left. Notice again the channel, it looks more like a python going that way. There are in fact two of them there. So again, bringing the negative curvature, positive curvature on the displays, strat cubes, and then you have your coherence brought on with the use of transparency. Now, many times what is going to happen is when you have a lower bandwidth of the input data, you may not see some of the features of your interest very clearly. But when you enhance the bandwidth and then run the same curvature, again you will be able to see those features in more detail, as you see on this channel to the right and this thin little channel seen here, and also some features that you see as indicated by the pink arrows. Again, some more displays from our horizon slice that I'm showing you from the coherence, most positive curvature in the middle and then to the right. And then on the lower rung, I have chair displays for the same data. Notice the differential compaction seen on the two channels, on the coherence and curvature and negative curvature. Now here are more displays for your information. I'm again comparing the incised channel seen here with the differential compaction that we have seen before, and we are going to see going forward. So notice positive curvature giving us the edges on the incised channel and the negative curvature giving us the Thalweg. So what I do is on the coherence I bring in just the negative values of curvature using transparency, and the positive values in red using again transparency. So I can play around like this, bringing in negative values, bringing in positive values, and that aids my interpretation. Now if I show you this display here, you see we are looking at two channels. One is indicated with the yellow arrows, meandering channel, and there is another one that you see here. And just by looking at this, you may not be able to tell me which one is which. But if I show you a plan view like this, I'm showing you the strat cube. This is a planar view, and this is at an angle, a plan view. Notice now you can make out. This looks more like an incised channel, and this looks more like a differentially compacted channel. I can confirm this. I look at the positive curvature displays, the long wavelength version on the left and high resolution or the short wavelength version on the right. Notice I see a differentially compacted channel because the positive curvature has a single lineament going all the way for the definition of the channel. And here I have two separate lineaments, and so this is a differentially so this is an incised channel, and this is a differentially compacted channel. I bring in coherence display using transparency, and notice again coherence does indicate. The coherence doesn't give us the definition of or the distinction between the differentially compacted channel and the other one, but the curvature, because it is a shape attribute, it can do that. So this is a signature of the seismic signature of an incised channel. This is a seismic signature for a differentially compacted channel, and similarly this one. So some more examples for your information. Again, a strat cube from the coherence showing us different crisscross of channels, and then what you see on the seismic data, that particular signature which I am indicating with my cursor. And positive curvature, long wavelength. Notice now it is indicating the same differential compaction of the main channel, and this is the short wavelength version. Notice it is a crisper definition. Similarly, negative curvature giving us the edges of the differentially compacted channel, and the higher resolution version seen here. And then you can bring in your coherence, and that gives you more definition, clearer definition along with the curvature. And this is the high resolution version, and so on. Now let's quickly have a look at the reefs, the Winnipegosis reefs that I mentioned earlier on in the presentation. So you're looking at a chair display where we see a reef, and this data is seen. Data is of coherence, and the vertical seismic is the seismic. And notice the yellow arrows indicating the edge of the reef here. There's a discontinuity feature also that is seen or indicated with the green arrow, and the differential compaction that you see over the reef is indicated by the blue arrow there. Similarly, I have another one example where I'm showing you the edges around the reef, a different example, and then differential compaction over the reef seen on the seismic data. Now, this type of a signature can be distinguished from again a circular feature that I see on the coherence, but a seismic signature is different. The seismic signature is different in this case because here we are looking at a salt collapse type of a feature. It is not a reef, though of course this circular feature on the coherence might indicate that this is a reef type of a signature. But when you go to the seismic signature, and this is very important, we must confirm each and every signature on the attributes with the seismic signature and convince ourselves our interpretation is accurate. So these are the salt collapse features that we see here, and that is giving rise to this circular feature. Now, in all the curvature examples that I have talked about, we refer to we refer to curvature as structural curvature because it is derived from the dips of the reflections. As I said, curvature is a shape attribute. So we first need to compute the dip and azimuth from the seismic data, and then make use of that to compute what we refer to as normally speaking curvature, but then strictly speaking it should be called structural curvature, both positive and negative. And that is what I'm showing you on the two slices or the two images to the left. But then there is another aspect that can be utilized. Instead of using the dips of the reflections, we can use the amplitude information. Amplitude information that we will look at. Instead of the dips, we will look at the amplitude gradients, and that is the direction in which some of the research has been focused. And look at the reef signatures here, Winnipegosis reefs. On the amplitude curvature, positive, it shows us a much better definition than what you see up here. And similarly, the negative curvature is showing me a lot better definition as compared with the structural negative curvature that we see in B there. So if we see such accurate and distinct features on the amplitude curvature, both positive and negative, the next thing to do is to confirm them with the seismic signature. And so here is a chair display which does indicate the definition that we expect to see on the positive on the for both the positive and the negative curvature, and that is what we see on this display. So to sort of conclude this talk, what are we saying? By understanding the depositional environment, differential compaction can serve as a lithology indicator. Channel features that are often identified by their meandering morphology on maps, they can be seen on the positive and negative curvature much better. Positive curvature anomalies over channel features indicate that these channels are filled with a lithology that is less compactable than the surrounding matrix, indicating the presence of a sand, or shall I say a sandstone. And if the channels are in the near shore environment and have been filled by rising sea level, there is a high probability that they are filled with shale, indicating that the sand should be found in the surrounding less compacted point bars and levees that express a positive curvature anomaly. And finally, the bottom line is that a clear understanding of the depositional environment and the effects of differential compaction, coupled with the high quality 3D seismic data and a modern seismic geomorphology workflow, they can all facilitate a rapid interpretation of subtle, perhaps overlooked geologic features of interest. With this, I acknowledge Seismic Solutions TGS, the company that I work for permitting all this work that has been carried out, and of course Geomodeling Technology Corporation, which is the software that I use for all my displays. With this, I thank you for your attention.